Hello, everyone. So today we are going to talk about out-of-order support in Prometheus, how we originally designed it and then implemented it. We should mention also that it was not only Ganesh and myself, but also Dieter Pletnik, which is not with us today. So first thing, round of introductions. So my name is Jesús Vázquez. I work at Grafana Labs right now as a software engineer. I have a past as DevOps / SRE / platform engineer and a bit of software development, but for the past 2 years I've been exclusively working as a software engineer at Grafana. I work on the query squad, which is very close to Mimir. We kind of do Mimir proxies, which are also open source. They are little components that sit on top of Mimir and allow you to write different metric formats into Mimir, like Datadog, Influx, and Graphite. The golden fellow in the picture is my best friend, Kaito. He couldn't make it today, but he's been all the time with me doing these slides.
Yeah. And for everyone watching the recording later, I'm Ganesh Vernekar. I'm a software engineer at Grafana Labs and also a Prometheus team member.
All right, so what is out of order? Big question. We thought about writing a quote and a paragraph, but we think it's best to illustrate it. But before we get to explain what this image means, I'd like to do this little exercise. So we're going to talk about out of order within the TSDB, and the TSDB is this huge list of things and little components that work together. So we're going to narrow our focus into the series level of the TSDB. So you can think it has a lot of series. We're going to talk about specifically one series only. In this case, it's one known by all, I think, HTTP request total. So this picture is illustrating 6 samples that are coming one by one in chronological order, from value 1 to value 6. The first sample has timestamp 0 or T0, and then the subsequent samples are coming with a bigger or a newer timestamp, like T0 plus 15 seconds, plus 13 seconds, and so on. The first 5 samples that we got are fortunately in order, so that's what you all see in your instances, usually. But the 6th sample that we got came with an older sample than the last sample that we appended. That is T0 plus 50. So that is 10 seconds older than the last one that we appended. That is out of order for Prometheus, and that is what we are trying to solve here. A bit of context here, and perhaps addressing the big elephant in the room, why add out of order support now? I think we need to add a bit of context to this question. For some of you, it might be maybe too late, like Prometheus has 10 years, why now? For some of you, it might be perhaps like it will make sense to have it now. And for others, maybe it's not needed. Like if we didn't have out of order before, why have it now, right? Well, I think we should recapitulate a little bit, and we should think that Prometheus started with its pool-based approach, and in that context, you only went to your services to scrape for samples every few seconds, like you would configure a scrape interval and go perhaps every 10 seconds or so. And so in that context, it's very hard to run by out-of-order samples. But as things move along and things scale up, the architectures get trickier. And many people in this room is managing clusters today where we not only have a single TSDB, but we have sets of TSDBs writing into other TSDBs, sometimes not using the pool-based approach, but remote write. So I think within this context, out of order starts to make sense, and we can run by some use cases. So we've made a list of the use cases that we've seen while we've done it. The first one is perhaps the most common one, which is network isolation. You can see So this happens sometimes when you have an outage or your cloud provider has an outage and then your service has no internet for a period of time. And so it batches up the metrics it has. And then suddenly the network comes in and you start sending everything. But because not all machines come at the same time, like you can run into out of order. Another example of network isolation is in the IoT space. Like imagine you have a farm, and this farm has 100 devices, and each of those devices is on purpose isolating from network connection to save battery. So but still it might be online gathering data. It's just keeping it, and then eventually it will establish connection and send it. And because of the nature of these devices, you cannot really control when do they send it. So like device 1 can wake up first, and then device 3, and then you get out of order between them. So I think for the IoT space, it's actually pretty natural to have out of order. And then another 2 use cases that we've seen, perhaps a bit more rare, but we've seen clients having them, like huge delivery systems for metrics. Like let's say you have a very large infrastructure with multiple clusters, and you'd like to have all your metrics funneled through a message bus that then delivers all the metrics to a huge TSDB. So message buses like Kafka kind of focus on delivery, not on order. So because of these, also having out of order is natural. And last, and perhaps the more rare of all, is aggregation of metrics. You can find yourself looking at 1 year of data, past data, and then maybe going week by week, quarter by quarter, aggregating data, and then wanting to write a point in time. Like let's say in Q1 I had that many whatever, and I want to write it at the end of the queue. And so that would be out of order as well, and something you could not do before. So for all these reasons, we thought that out of order added value, and that's why we're here. So now we are going to dive in on how we do this, or how we did this. And we're going to do it in an orderly manner. We're going to first focus on the writes, then on the reads, and then Ganesh is going to go through compaction and write log. So the first thing we looked at in the TSDB was how writes are happening right now. And what we saw is that for a single series, in this case, HTTP request total, there was an in-memory head chunk where samples were being appended. Because Prometheus made the assumption that every new sample was newer, like we could always append at the end. We didn't need to look where to place it, so we will always append at the end. This is very performant on the writes because you don't need to look anything. You just write at the end. Only need to look on the series. Because of these, you could also compress the data and keep it compressed. And so when a sample comes in, you just encode it and compress it at the end. You don't need to decompress anything. So that's very nice because it allows you to keep a small memory pressure while you keep ingesting all the data. And one thing important is we like to keep the samples ordered by timestamp for querying, because we want to also provide fast reads. We want samples to be ordered, and that way we can then go through them faster. So now, how do we write out-of-order samples? So basically, based on this idea of having an in-order head chunk, we said, okay, so what we need is another out-of-order head chunk, but this time, we couldn't make the assumption that samples would be ordered, on arrival. In fact, out-of-order samples can be out of order amongst them. You can get a 1 week old sample and then 2 days old sample, or if you think in minutes, half an hour old sample and then a 5 minutes old sample and then 1 hour old sample. So you always need to find what's the place for that sample. This kind of has a couple of downsides. One of them is that you cannot keep data compressed. Otherwise, when the sample comes in, you have to decompress, find where it goes, place it, and compress again. That kind of adds a lot of overhead to the writes. So we made a trade-off of, okay, we keep it uncompressed. That will put a bit more memory pressure, but it will be more performant on writes. And we put another system in place to lower the memory pressure, but just remember that it's uncompressed data for now. And on arrival, we kind of look where the sample goes, and then we order the entire list of samples. And the image, you will see that we had 3 initial samples, and the 4th comes in. And because of the timestamp, it goes in the 3rd position. So we have to place it there and then move the other sample to the right. And so that's just remember that now our TSDB for each series is going to have 2 different heads, the in-order head chunk, 2 different head chunks, the in-order head chunk and the out-of-order head chunk. But we're going to be able to ingest everything. There will be some logic in the appender part of the TSDB that based on the sample that arrives, we're going to check the timestamp and we're going to know whether it goes to one of the heads or the other. Right. So now onto the reading part. In here, we also checked how reads were happening. And there's where we saw, you don't need to understand the code or read it. Just remember that the TSDB already has some abstractions in place that are very useful, that go by the name of index reader, chunk reader, and block reader. And the index reader gives you index data on the chunks, and the chunk reader gives you the actual samples, and the block reader kind of wraps both interfaces for the upper layers. So we leveraged, so we saw that the in-order chunk was implementing, or there was an implementation of these interfaces so that you could read the in-order head chunk. And so we basically used this approach for the out-of-order, and we implemented these interfaces again only for the out-of-order head chunk. So this image represents more or less what happened in the code base. The out-of-order range head box that you see there is what was added, and the other boxes already existed. So whenever a query comes in, the querier goes, which only knows about the block reader interface, goes to all the available blocks it has, and that includes persistent blocks in the file system, or the head block. And the head block has now 2 heads, the range head and the out-of-order range head. And so we would go for the in-order head to one and for the out-of-order data to the other. There is this comment we've made on the out-of-order range head, which is that it compresses data. Remember that data in the out-of-order head chunk is uncompressed because we need to order on the writes. But the query expects data to be compressed. So every time there is a query, we have to compress the data for the upper layer and send it. This has a bit of a CPU overhead, and it's something we are maybe planning to improve, but Ganesh will talk about that later. And so to illustrate a simple query, we have this example. So we get a query on HTTP request total for the interval T0 to T0 plus 60. And what the querier is going to do is going to go to the head block and go to each of the head chunks, the out-of-order and the in-order head chunk. And as you can see there, it's going to return all the samples ordered. So that's the magic underneath. Now we have a place to put all the samples, and the query is going to go through all of them, and it's going to return a single slice of order samples for the client.
Yeah. So now that we have seen the writes and the reads, there is another process in Prometheus called Compaction, which does the maintenance of data in the background. For the in-order data, the compaction cuts a new block every 2 hours from the in-order data. So every 2 hours, you get a single block which spans 2 hours. But in case of out-of-order data, there is no limit on how old a sample can be. And in Prometheus, we try to keep the block 2 hour aligned, like the start time of the block and the end time of the block will be aligned to some 2 hour UTC. So because of that, In this example, I take timestamp as 10 minutes starting from UTC 0, and it spans all the way to 300 minutes, which is like 4 to 5 hours apart. And if you see, it fits in 3 blocks, which are 2 hour aligned, which is 0 to 120 minutes, 120 to 240, and 240 to 360. So as a result of this, every 2 hours when we run the compaction cycle, from the out of order data, it can produce more than 1 blocks. In this example, there are 3 blocks. And the block ranges need not be contiguous. If there was some data missing in between, there will be just 2 blocks, for example. And if the data was 1 week old, there will be just 1 block for that range of data. And once these blocks are produced, TSDB already takes care of them. Like if the blocks are overlapping with other blocks, it merges them together. And until the meantime, Prometheus can query overlapping blocks. So that's about compaction. And there was one more artifact that we introduced on the disk. You might already know there is something called write-ahead log, where for every write that's coming in, we first log it in this write-ahead log. And once that is done, we actually store it in the TSDB. But when it comes to out-of-order sample, you cannot say if a sample was out of order until it has been ingested in the storage, because due to misconfiguration, you might be getting writes for the same series from multiple sources. And you might have thought the sample is in order when you checked it first, but when you go to write it, it can go out of order. So we introduced something called write behind log, where you log things once the append in the storage has been done. So right now the write behind log only has the out of order samples, and it is designed in such a way that all the series definitions and everything that's required to restart has to first go through write ahead log, and only then your write behind log will be replayed. So this adds a little bit of overhead on the restart depending on how many out of order samples you have. But yeah, if there is no write ahead log, then the out of order samples from write behind log will also be discarded, because we don't know which series to match it to. So that's about the disk artifact. Now let's talk about how much resource it's going to take you to run this. So it depends a lot on how your out of order data is incoming. For example, it depends on the percentage of your active time series that are getting out of order data, because there is some initial overhead to getting out of order sample. The out of order head chunk that Jesús talked about, it's only initialized if you get out of order sample for that particular series. So if you have a big percentage of time series getting out of order samples, it can have a bit of memory overhead. But in practice, we have seen even with 10% or more of time series getting the out of order data, there was not much noticeable difference in the memory usage. Also, the rate at which out of order samples are incoming also matters. Like if a time series is getting more out of order samples, then it will take more memory. It's capped up to some amount, but it still takes a little more memory. And to keep the slice sorted, there is a little more CPU that is being used with more out of order samples incoming. Also, as Jesús mentioned, when querying out of order samples, we compress the uncompressed chunk and then pass it on to the later stages. So if you are querying too frequent, and if the query is touching this out of order data too frequently, then the recompression of the uncompressed chunk is going to take a bit of CPU. And in practice, in production, we have seen that more often than not, you will see a little bit increase in the CPU usage and not much with the memory. And when it comes to performance, we haven't really seen any performance degradation as of now. We mostly tested this as part of Mimir, because we also added in Mimir and we are running it in production. There we did not see any difference in the write latency or the read performance. But there, the data is always overlapping. So we are always deduping the samples, so we don't see any difference in reads. It's possible in Prometheus, because you always have in-order data. Once you start getting out-of-order data which overlaps with the existing data, it's possible your queries might be a little slower for some time until the compaction takes care of making all the data not overlap. So how do you enable this feature? So from version 2.39 onwards, we have added, like this feature is available, and though you don't need to use the experimental feature flag explicitly on the CLI, the feature is right now experimental, and you configure this in your file, the configuration file, which means if you want to change this out of order window, you can do it during runtime. So let's see what this out of order time window does. I said there is no bound in how old the data can be ingested, but still we want to have some kind of protection against it. So here, when I say 1 hour of out of order time window, it means the out of order samples will be ingested if it's in the last 1 hour or 1 hour with respect to the latest time in the entire TSDB. So if the TSDB has, let's say, the last timestamp as 100 hour of the Unix timestamp, then out of order samples will be ingested between 99 hour and 100 hour. And if you set this to 12 hours, then you can ingest up to last 12 hours of data. It also solves another problem, not just out of order. There is another thing called out of bounds. If the TSDB has the latest sample as 100 hour, then TSDB won't allow you to ingest any sample that is beyond 99 hours. Like if it's more than 1 hour old, then TSDB will simply reject it because of some complications with the compaction, even if it's an in-order sample. So with this, even that problem is gone. Like you can ingest up to 100-year-old samples, why not? And there was another thing, like if you wanted to ingest some sample in the future, let's say you ingested a sample which was 24 hours in the future. Because of this out-of-bound logic, what it will do is, it will only allow you to ingest samples from 23 hours in the future to 24 hours in the future because of how TSDB worked. So if you wanted to ingest samples in the future, you can't ingest samples in the present. So this takes care of it, where if you expect samples to be like, let's say 24 hours in the future, you can set this out of order time window for 24 hours. So you get the samples for the future, and the 24-hour out of order window will take care of samples in the present. And this way, you can ingest any sample in TSDB irrespective of what timestamp it has. And we have a design doc where we first discussed this with the community, and it has a lot more details on how things work underneath and what components needed to be changed and how they needed to be changed. So if you are interested in learning about this more, we'll be publishing these slides later, and you'll have access to this design doc via this link. Or you can find it in the Prometheus website. We have a page for design documents, and we have the design document there.
And last, just a few notes on the future of out of order. So the first thing is to drop the experimental from it. Yeah, I don't know if you mentioned it enough, but it's experimental, so be careful if you use it. If not, you can fall back to the LTS version. But on the bright side is we are using it in production at Grafana, and it's going well. And I've been talking to people that's enabling it. It's enabling it on the pre-production systems, and it's also working. So we are certain that we will reach that point in the future. And then, of course, we cannot just file a PR and remove it. We need more production time with the feature. But we are on the good track. The second point is what I mentioned before, because the out-of-order head chunk is uncompressed, but we are always returning compressed samples to the query. That has a CPU drawback. So we want to explore the idea of, so we didn't do this, we kind of were limited by the existing code base, and we didn't have time to improve it. But now that this is merged, I think we have time to investigate and see what can be done here, and perhaps improve the read path a little bit. And then the last item on the list was actually Bartek's idea. This came out in one of the storage dev calls, I think. But basically, we said, all right, so the out-of-order change is adding quite a lot of code to the TSDB. So you could say that the complexity is rising. what if we merge both paths? What if we do something in the TSDB that it, I don't know, adapts and is able to ingest both in-order and out-of-order data without needing an extra head chunk and all the extra code we added. And so that perhaps on the long term would yield a more maintainable code base. So it's just something we talked about, but perhaps something to consider for the future.
Yeah. So I want to add a note about the experimental thing here. In Prometheus, we approach experimental flags in two ways. One of them is, for example, native histograms, where we expect things can change. It's a very big breaking change, so things can break in a way that it's not backward compatible. So we put experimental tag on that. And in some other cases, the changes are significant, and though we don't expect it to break or change in any way, we just want to be a little cautious and give it a little bit more time in the community before we flag it stable. So the experimental here is the second kind, where we don't expect it to break. We think it is stable. We have been running it in production for quite a while now with a very high scale. So the experimental here is just that once we gain enough confidence, we'll just drop the experimental flag. So don't worry about trying this in production. Yeah, so that's it. Thank you.
Thank you. Any questions? Oh, two in this area. Hi. First of all, thank you for your talk, and thank you for right behind log concept. It's just like I'm full of joy. My question is, like, have I understood right that at the moment when you get the first out of order sample, you have two head chunks, as so like each read request internally ends up with two kind of sub requests? Is like, have I get it right, or?
So yeah, I think I get what you're saying. Let's say you said if your first sample is very old.
Like if you have at least one
yeah.
out of order sample, at that moment your Prometheus change behavior and starts doing two subqueries to TSDB.
Right. So it is, but one of them is very, like, let's say they are very fast, because if there is no sample, you will get right away a no, there is no sample, because both head chunks are tracking the mean and the max time. So whenever the query comes in and says, give me the last 5 minutes of data, it would go to both places, and then one place won't have any data and will return like right away nothing, and then the other would just surface. Yeah.
So this thing where it's split into two requests, it happens internally in the TSDB, but if you are using the TSDB, you won't face this. Like, you ask the TSDB for samples in this particular range, the TSDB takes care of merging and querying things internally. So it's just running in a single process and abstracted away.
Thank you. Thank you.
Thanks for your talk. Very interesting to know how Prometheus implements out-of-order samples. And my question is it possible to set the out-of-order window to the retention period of Prometheus? Is it possible? And whether this affect performance of Prometheus?
Like, it doesn't affect the performance much. The only thing that will happen is if you have data which is too old, and if you are querying, it will just merge the query results, like the samples from the out-of-order data, with the block which is too old. But I don't think it will affect any performance. And if the sample goes beyond retention, I think it will first ingest in the out-of-order sample. It gets compacted into a block, and the retention will take care of removing the sample immediately.
Any other questions? Alrighty, thank you so much. Oh, there's one. Sorry. One more question.
One last thing. When you write the out-of-order blocks and you remote write them back, is this do you see more traffic because of the new extra blocks based on the rate of out of order incoming samples, or have you seen this kind of behavior?
So out of order will only write samples from the write ahead log. It won't look at the blocks. Basically, whatever samples TSDB ingests, it remote writes. So if you are ingesting more samples now, if it's out of order or in order, it's going to increase the remote write traffic. If you happen to have the samples in order or the out of order, it won't make a difference. It will be the same remote write traffic.
Alrighty, that was the